No, no, no. I just wondered why you were all the way back there, but that's fine. Okay, so we were into the last class looking at these common translations of the conditional statement, the if-then statement. You won't have to. We're not going to use any of them except either if-then or some implied version of it. So I'm not going to spend too much time on that. I'm going to talk about biconditionals. So the conditionals, if statement P, then statement Q. The biconditional is if P, if and only if Q. And you use the double-headed arrow to represent that particular logic operation. And it turns out that the biconditional is equivalent to if Q then P and if P then Q. So what this part right there, let me put it on one page, it's a little bigger. If you do the truth table for this particular operation, and I'm using, let me just erase this because it's using the other way of generating truth tables. So let's use the normal way. So we need 2 columns for P and Q. We need 1, 2, 3, 4, 5, 6, 7. So we need 9 columns, and we need 5 rows. So let's do that. We need 5 rows because there's P and Q. 2 squared is 4 plus 1 is 5. And I need that. So let me just, it's called biconditional because of this, because it's a conditional in both directions. If P then Q and if Q then P. So if one's true, if it's true one direction, it's true the other direction. That's pretty much what they're saying. So now I have my table, my truth table, to generate this, just to show you what the final truth value is for the biconditional as written this way. So we're going to have a column that has P, one that has Q. So that's because we just have the 2 letters. Then we write the whole logic expression. If Q, then P, and if P, then Q. So the first 2 columns we just fill out with our normal arrangement. And a lot of this is just copying stuff down. So once we fill those in on our normal manner, we're just going to copy down P and Q in the appropriate columns. So this is the Q column. So we write Q again, true, false, true, false. We write the P column, which is true, true, false, false. The P column again, which is true, true, false, false. And the Q column, which is true, false, true, false. Okay, so that's just copying stuff. Then we use the conditional for comparing these 2 truth values, and we use the conditional comparing these 2 truth values. So the conditional by itself is, what I'm trying to do is get rid of that little box. I don't know why it does it. Oh, there we go. Good. So the conditional says that the conditional is only false if the first truth value is true. So these both have the first truth value true and the second one is false. So this is the only false that we get. Everything else is true for the conditional statement. And you do the same thing over here. The only time an if-then statement is false is if the first one is true and the second one is false. So that one is the false one, and the other 3 are true. And then we compare these 2, which are the result of the left-hand side and the right-hand side, and we use the rules for the and statement, which says that the and is true only if they're both true. So we see we have true and true, so that one's true. And we get to the last one, we have 2 trues, and the other ones contain at least 1 false. So So that's what the truth table for the biconditional is. It's true if they're both true, and it's true if they're both false. So they kind of have to match up. The truth values have to match up for the biconditional statement to be true. And so I looked up online and said, what's an example of a biconditional statement that, and everybody seems to use the same example, so it seems like I should use the same example. And it has to do with geometry. So a triangle is isosceles if and only if two sides of the triangle have equal length. It's almost like a definition, because an isosceles triangle is a triangle with two sides that have the same length. So a triangle that has two sides of the same length is an isosceles triangle. So that's the case where both of them are true. If you looked at, therefore, if a triangle is not isosceles if and only if the two sides of the triangle are not equal to each other. Okay, so both of those statements are true. You have the case where both of them are true and both of them are false, and the statement, the biconditional statement, is true. But if you said a triangle is isosceles, so if a triangle is isosceles, but then you said they didn't have equal length, so that wouldn't make any sense. And really, biconditional statements are mostly limited to math situations. I'm trying to think of another one. Well, I'd have to use a calculus example, which you guys wouldn't understand what I'm saying. So I'm just going to, in general, most the biconditional statements involve math definitions to some extent. So we're introducing it. I'm not going to test you on it. If I did test you on it, you just have a different truth table to use when you compared two columns. So it's not that it's any harder, it's just not that it's not used very much. And I think there's, here's an example. Is the following statement true? So it is a biconditional statement because it has this if and only if. 8 plus 7 is not equal to 15 if and only if 3 times 5 is not equal to 8. So just from a truth value standpoint, the first statement is false. 8 plus 7 is equal to 15, so 8 plus 7 not equal to 15 is false. And 3 times 5 is 15, which is not that. So the second statement is true. So just using the truth table, one being false and the other being true, the biconditional result is false. Yes. Does not be on the test. Will not be on the test ever. Okay. So, yeah. Because I'm looking at this, and to me it doesn't make a whole lot of sense, from a math standpoint. So that's why I'm just saying most of the time it's used in definitions in math theorems of some sort. So, and another triangle example. A triangle is equilateral if and only if all three sides of the triangle have the same length. So that's, again, it's just a formalized way of creating a linkage that's always true. Okay, then we have just some more definitions. So you have statements that are you have two statements that make up a conditional statement. You have the first statement and the second statement. The first statement we call the the antecedent and the consequent. Okay. So, but in general, if you just look at two statements, whether they're part of a conditional statement, conditional or a and or whatever it is. Consistent means that the two statements can be true about the same object at the same time. Two statements that are contrary is they cannot be true about the same object. So I'm going to just use an example, two examples, one that's consistent, two statements that are consistent and two statements that are contrary. So here's two statements. That animal has 4 legs. That same animal is a cat. So can those both be true for the same object? Yes. Okay. An animal, you look at an animal, you see it has 4 legs, and that animal can also be a cat. So these two statements are consistent. They can apply to the same, they can both apply to the same object. So we can say this is consistent. Now, contrary is something like, I'm just going to say it verbally, but I'll give you a written example in a second. It's different. That person is alive. That person is dead. Okay? So those statements can't be consistent because you can't be both alive and dead at the same time. So you can. So that would be an example of example of a contrary statement. So here's another example of a contrary statement. And let me just, if anybody's still copying down, I'm going to copy this over and just move it right there so you can compare the two. So this is another. This number is a whole number. This same number is a negative number. So by definition, a whole number is positive. Therefore, a number cannot be both a whole number and a negative number. So that's what would be an example of contrary statements, because they can't both be the same. 3 is a whole number, but 3 is not can't be a negative number. So you got a couple examples that you'll do for homework. Again, none of what we're talking about today is on the test on Wednesday, which leads me to talk about the test, now that I'm thinking about it. So let's go to Blackboard. Yeah, so this is what is an example of biconditional statement. So if you go to Content, Test Reviews, you'll see there's two things. There's Test 2 Review. It's fairly long because I go through an example like each problem on the test. I just choose different, truth tables. I'll do a particular kind of statement. You just have to do a different one. So Venn diagrams. I'll do an example like the one on the test, but not exactly like it. So you want to watch that. I also did a review last year on truth tables, just another review on truth tables. So there are 3 examples in the review. If you need some more help with truth tables, then you can watch the additional video on truth tables. And I don't know how long this thing is. I'll just open it up. You can tell by I thought that might happen, because they were so close to each other that of course that would be the end of their. Well, you would think that would be the end, but you never know. Yeah. Okay, so this is a summary. It's in your book. It's just a summary of the truth tables, but just doing it verbally. We've gone through this before, so I'm just going to review it. When you negate something, you change the truth value, true to a false and a false to a true. We've done that many times. A conjunction, which is an and statement, is true only when both the first and the second statements are true. The or statement is only false if both the first and the second statements are false. The conditional is only false if the first statement is true and the second statement is false. And the biconditional is true only if they're both true or they're both false. We're not worried about that one. So this summarizes everything you need to know about filling out truth tables. Those are the basic truth table rules. Biconditional. Okay. So I don't know if I assigned that. Did I already sign 2.4 or not? If I haven't, I have now. So I think this is due next, so it'll be due next Monday. So I'm probably going to give you an hour to do the test on Wednesday. So we are at the first 15 minutes. I know you're like 15 minutes, why don't you just let us take the test, but I'm not going to do that. So the first 15 minutes will be lecture, then you'll get your test. So you'll have an hour, plus you may have another 5 minutes or so, 5 to 10 minutes before Mr. Shaver comes in. So I'll give you as much time as I can, but after, so you get about an hour and 10 minutes, I would expect. Yeah, Mr. Shaver, when he comes in, we'll have to leave. So. Now, there have been people in the past who have said, you know, I'm just a slow test taker. Officially, you have to have a documentation about that. But if you talk to me about it, if you feel like you're one of those kinds of people and you still need a little extra time, I might be able to help you out there. We'll let you take it to the library. But okay, so we're moving on. Section 5. So the last two sections of Chapter 3 are about determining whether arguments are valid or invalid. So Section 5 uses something called, I was going to say Euler, Euler diagrams. So it's, and they're for a specific kind of argument that involves the word all. Okay, you'll see it in a second. But before we do that, so what we're going to do is we're going to have an argument that consists of 3 parts, and we'll find that that's the normal arrangement. You have 2 statements, and then you have kind of like a conclusion or result of the argument. And part of, in arguments that we can analyze using the Euler diagram, we basically have kind of a general statement, like we did with deductive reasoning. You know, there's some kind of rule that applies to everything under all conditions. There's a second statement that applies to more of an individual, a subset of the general statement. So we're going to use that kind of reasoning in these arguments. And we're going to make a conclusion about whether the argument is valid or invalid. So an argument is valid if the fact that all the premises are true forces the conclusion to be true. So an example that we've used before relative to grades and results or effort. What did I say? If you study hard, you will get an A. So if you study hard, you will get an A. Okay, that's kind of like the general statement. Then you study hard would be the second statement. Therefore, you get an A. So there's three parts. There's the general rule that I've applied. They're saying specifically for you, you've done something that relates to the original statement. And therefore, the conclusion is you get the appropriate result. So the premises in that case, there's two premises. If you study hard, you will get an A. That's one premise. So if that's true, and then you study hard, which is the second premise, if that's true, the conclusion has to be true, or it's not a valid argument. Somebody's lied to you. Now, as far as what is an invalid argument, it's an argument that's not valid. Okay, so we call an argument that's not valid, we say it's invalid, or we call the argument a fallacy. So those are the words we're going to use: a valid argument, an invalid argument, or a fallacy. So we don't say a fallacy argument. It's just a fallacy is an invalid argument. So the way Euler diagrams are was we use circles. And it says one means of checking validity is using Euler diagrams. So we have these circles, and we label the circles according to the first statement that we make, which is this general statement about something or other. Then we use the second statement to place a little X somewhere, whether it's in the big circle or whether it's specifically in the small circle. And based upon the position of that X within the circles, we can make a conclusion that is a valid conclusion. So let's just, it's hard to explain unless we do an example. So we're going to do an example. So here's our, these are our premises. First premise is all disc jockeys play music. The second premise is Flash Phelps is a disc jockey. And this is our conclusion. And we're going to use this diagram to show whether this is a valid argument or not. So here's our two circles. We're going to try to represent what this is saying by labeling the big circle and labeling the little circle. So all disc jockeys. So the first part refers to the inner circle. So I'm going to put a little thing that says disc jockeys, which is kind of funny because I guess nowadays you wouldn't be calling them a disc jockey because they don't have discs. What would you call them? Yeah, they still say DJs, but yeah, disc jockey was because that was the guy that was putting the records on the record player. Okay, so disc jockeys, all disc jockeys play music. So the outer circle is people who play music. We'll see how that applies now. So that's what you would do. So you can see all disc jockeys. So the circle that represents disc jockeys is within the larger circle of people who play music. So all disc jockeys play music. Okay. You might have, because that's what disc jockeys do. Like, is that a Geico commercial? Seems like Geico commercials. You know, you might have some other circle over here that represents, what would it be? Teenagers. Okay? So some teenagers listen to music, some don't listen to music. It probably would be more like this. We're assuming that they can't work as disc jockeys, or there'd be some overlap between them. So by using the word all, I get the small circle and the big circle. And you have to be able to do that. So I'm getting rid of that. It was just so now we use the second statement to draw a little X. Flash Phelps is a disc jockey. So because Flash Phelps is a disc jockey, I can put him in there. So Flash Phelps is one example of a disc jockey. There are other people, you know, whatever. Wolfman Jack. Pardon me? Why did I take that away? Oh, that was just because I was using that as an example of how you might represent something that some people play music and who people don't. I was just trying to show that as an alternative to how all fits all inside of it, because that's their job, so they have to play music. So, you know, everybody who's a disc jockey is going to get a little X inside here that represents that they're a disc jockey. So by the second premise, this is the second premise, I can put a little X to represent that. Now, the conclusion has to be supported by what I've got here. Well, because Flash Phelps is inside this circle, and this circle is inside the big circle, then this is a valid conclusion, because if Flash Phelps is a disc jockey, that makes him in the big circle, therefore Flash Phelps plays music. Okay. Now, if I stuck Flash Phelps out here, then I couldn't make that conclusion. That would not. We'll do an example that doesn't work. So that's the basic idea. You take the first statement, label the circles, use the second statement to put a little X somewhere, either here or way out, and then you see whether that X agrees with what your conclusion is. So here's another one. Very appropriate for what we were talking about. So it says all. So since it says all, we probably can use this technique. So all politicians lie, cheat, and steal. So what I can do is I can put politicians here. Some just lie more than others. So that's politicians. People who lie, cheat, and steal. So you could put, you know, maybe, don't write this down, Harley. So, you know, you could put somebody like, you know, the mob or something like that. People who are in the mob. Some of them could be politicians. Some of them, you know, you figure people in the mob, that's their job, to lie, cheat, and steal. So, you know, that would be an example of another case where you could draw a circle, but I'm not using that. So that's allowed me to label the big circle and the little circle. Now the second one, that man lies, cheats, and steals. So where can I place the X? Well, theoretically I could place it here, but I can't specifically do that because it doesn't say he's a politician. If these were switched, then it would be, I could stick, you know, if this were the second statement, that man is a politician, then I could put an X there. But because it doesn't specifically force me to put the X in there, I'm going to put the X there. Because it could be either there, or it could be there, it could be anywhere, just in the big circle. So because of that, the conclusion, that man is a politician, is not, this is not a valid argument, because it hasn't forced me to put the little X inside the smaller circle. So in contrast to that, if this were my argument, so this is an invalid argument. So how would I rearrange that? I can't spell, argument. If it were this way, again, it would be labeled. The first statement would allow you to label the circles the same way. But the second statement would say Bill is a politician, so that would mean here's Bill. It forces me to put an X inside the smaller circle. as a consequence, the third statement, which is the conclusion, has to be true. So Bill is somebody who, because he's a politician, he's a person that lies, cheats, and steals. Whereas this one, so this is an example of a valid argument because of that fact. So that's how they work. So let's do another example. Now, it doesn't mean that invalid arguments can't be true. It just means that, so you look at this and you're like, yeah, that's true, so it must be a valid argument. Well, that's not okay. Has to pass this test to be a valid argument. And the problem here is all these use of alls. You know, you'd see that I'm using all multiple times. So we'll do the invalid one, then we'll do the valid one. How would it have to be written to be a valid argument? So all chickens have beaks. So the outside circle would be things that have beaks. And the one of this inner circle here would be chickens. So that's the first statement. Things that have beaks, chickens are things that have beaks. Other things have beaks, like other kinds of birds. All birds have beaks. So that doesn't really allow me, using the word all, you can't put a little X to represent all. You can only use a statement by itself without the word all to actually put an X. So that's problematic. And you might say, well, can't I just make this thing bigger, and you know, chickens are kinds of birds, so I can stick that in there, and then that's true. But that's using prior knowledge, because I know a bird. Well, actually, yeah. So that's not, I can't do that. All I can do by the second statement is I can say, well, I know that if I draw a circle to represent birds, all I can do is make sure it's in the bigger circle, but I don't know whether chicken's a bird or not, because that's not stated at all. So it has to be explicitly stated. That's why it's a true statement, but it's only true because you're making implicit assumptions about things. So the second statement, all that does is allow me to draw another circle, and therefore when it says all chickens are birds, that would be if I put the chicken circle in the bird circle. But that's, again, assuming that that's saying that chickens are birds, but I don't really know. I mean, I know that, but the argument doesn't allow me to do that. So it's a little, what's that? Yeah, so this is an invalid argument. It is a true statement, but it's an invalid argument because I can't put a little X, force that X somewhere. It's probably because if you saw a statement with lots of all statements, it's probably too sweeping to narrow it down and make it work. So what would be a valid argument involving chickens and birds? So this is one. So I still have my all statement. All chickens have beaks. So the chickens are inside here, and the outside circle represent things that have beaks. So that's first statement. Second statement, Bill is a chicken. So that would allow me to put Bill inside the chicken circle. Therefore, because Bill is a chicken and all chickens have beaks, then Bill has a beak. Okay, so this is a valid argument because I can use the second statement to put a little X to place me inside the small circle, which by default puts me in the large circle, and therefore that statement is true. So this is a valid argument. There was some argument. There was a political argument the other day. He keeps saying that, and everybody says, "No, you can release your taxes," and he keeps saying that over and over again. Yeah, the truth doesn't matter. Yeah, yeah. Yeah, what was there? Some argument. It was Trump related. So I'm going to say something that doesn't need to be recorded. Yeah. So guys don't tend to say that kind of stuff. Okay, so and then there are other kinds of arguments which are using other terminology to represent a group of something. So this is just an example. I'm not going to test you on it. Mostly what you're going to need to understand is a standard Euler type argument that you saw. I'm not going to put all, use all every time. It's basically you have a statement that involves all. The second statement allows you to put the X somewhere, and then you have to determine whether the third statement is justified by that. But here's an example of all people who drive contribute to air pollution. So let's see if I can write that particular, and actually it's on the next page. So let's see, all people who contribute. Okay, so this would be people who contribute to air pollution. All people who drive. So this is people who drive. No. Okay, people who contribute to air pollution. So all people who drive are people who contribute to air pollution. Then the next one says all people who contribute to air pollution make life a little worse. People who make life a little worse. So that's what the second statement allows you to do. All people who drive are people who contribute to air pollution. All people who contribute to air pollution are people who make life a little worse. Then you have some people who live in the suburbs make life a little worse. So the sum wouldn't allow you to put a circle within a larger circle. Some means that it's going to be over here somewhere. People who live in the suburb. So people who live in suburb. Now we don't know whether this thing goes, extends over here, might be like that. Because people, you could say, well, all people who drive must live in the suburb, but then you have retired people who don't. So, it's probably it's not going to be entirely enclosed, but it's probably going to be something like that. Then it gets really crazy. Okay, so anytime you use words like all too much or use words like some, using the Euler diagrams is not very useful. That's the gist of the whole thing. And this is the conclusion. Some people who live in the suburb drive. Well, I made that assumption here, but I really don't know where that thing overlaps. All I know is that the sum means that this thing overlaps with make life a little worse. So all that allows me to do is say this thing intersects somewhere. It could be intersect there, could intersect there, could intersect there, go like that. So there are a whole different places this circle that represents some people who live in the suburb, and so that doesn't provide you any kind of accuracy. Again, the statement is probably true. Some people who live in the suburb drive, but the argument is not valid. The bottom line, as I said, is when you have a lot of existential qualifiers, like all or some, these aren't very useful for validating arguments. So that's it. That's all you have to do. So there's not many problems associated with this. I might put one problem on the test. It'll be a fairly straightforward example. It won't be a off-the-wall example. Okay, what time is it? 1:48. Okay. So the last section is going to be about arguments as well. And we're going to use truth tables to prove whether an argument is valid or not. So this is sometimes hard to convert from a statement to circles. Using truth tables is pretty straightforward procedure. Must be nobody can take me today. Everybody has to go out. I can't take him anymore. I've got to leave. Just kidding. Okay, so section 6 is analyzing arguments with truth tables. So the general setup for arguments, we've just talked about this, but this is a more formal introduction. You typically have two premises. Then you draw a line to show that those are the premises in the argument. And then under that, you draw your conclusion. Yeah, we're on section 6 already. You already missed the notes, huh? Yeah, that's right. You snooze, you lose. So here it is. The premises are linked with an AND statement. So we have two premises. They're basically, they either can be just a statement, like, again, using the example, if you study hard, you will get an A. Okay, that is a compound statement. That's one premise. And if you study hard, and I studied hard is just a statement. It's not a compound statement. It's connected by an and. Then the last statement is I studied hard. So let me repeat that. If you study hard, then you'll get an A. Premise 1. You studied hard. Premise 2. I got an A. That's the conclusion. Okay. So you connect the premises by, the two premises are connected by an and statement. The premise can include an if-then part, so these are not just, sometimes they're just statements, sometimes one's a conditional and one's a statement. And then you connect the premises to the conclusion using an if-then statement. So it's premise and premise implies, or if-then implies means it's a conditional relationship conclusion. This will become important when we construct our logic statement and we check to see whether we apply filling out truth tables to get a result, and the result, if it turns out that they're all true, the result is all true, then it turns out it's a valid argument. You'll see that in a second. So here's an example. It's like sort of like the study hard and get an A question. So the argument is, if Julie Nem, this is from the book, I didn't make this person up, if Julie Nem works hard, she will get a promotion. So that is a conditional statement. If Julie Nem works hard, then she will get a promotion. So that's what we call the premise. So I'll just write that in a different color. This is a premise. The second premise is just a statement. Julie Nem works hard. And therefore, which is kind of like then, therefore, Julie gets a promotion. So that's the conclusion part. So individually, if I wanted to write this compound statement in symbolic logic, if Julie Nem works hard, then she will get a promotion. Premise 1, it's if P, then Q. The P statement is Julie Nem works hard. The Q statement is she will get a promotion. So it's if P, then Q. So that's premise 1. Yes. Yeah, I mean, if you switch them, would that mess up the validity of the argument? You can do that, and you can probably see, you know, if I took Julie gets a promotion second and Julie Nem works hard as the conclusion, that might be all those statements may be true, but the argument may be invalid. So we're going to see if this organization of the arguments, these two premises and this conclusion are a valid argument. It seems like a valid argument if you just looked at it, right? We've looked at it before. You work hard, then you get an A. I work hard, I get an A. Okay, same kind of thing here. We're going to show how you can use symbolic logic to prove that what your hunch is correct, because there are cases where your hunch may not be correct. Okay, premise 2 is Julie Nem works hard. I don't know why I didn't hard enough, so I need to put that. Julie Nem works hard enough. That statement, that's a single statement. It's a premise. So how do you write that? Well, it's just P. It's just the statement P. Julie Nem works hard. Julie Nem works hard enough. So that's the second part of the premise, or the second premise. And then the conclusion is Julie gets a promotion, which is just the second statement in the if-then statement. So that's just Q by itself. So we've got a conditional, a statement, and a statement. Then we put all those together into one complete logic statement. So what we said was that we said the premises are linked with an and statement. The premises are linked to the conclusion with a conditional statement. So using that rule, the final logic statement for this entire argument is if P then Q, so that's the first premise, put it in parentheses, connect it with an and to the second premise, and then connect that to the conclusion with a if-then statement. So that is the logical argument that represents this, or logic. This is the symbolic logic which represents the original argument. Now at this point, all I have to do is make a truth table and see what happens. So let's do that. So we need a truth table. We need two columns for the P and the Q. We need 1, 2, 3, 4, 5, 6, 7. 7 additional columns for the logic statement. All these parentheses, those are just things to group things together. So we're also going to need 5 rows because we have two statements, P and Q. So we need 4 for the truth table and 1 for the header. So it's going to be 5 by 9. So let's fill this thing out. 5 by 9, there it is. Let's put it on one page. So, first two columns, as always, the two statements, P and Q. Then we're going to write the logic statement. Again, the parentheses and the brackets don't take up space in this table. So we got that part, then we have and P, and then we have our conditional Q. So that's the logic statement for our argument. We fill out the first two columns normally. Then we copy down the columns that are involved in the actual logic statement. So they're all just P's and Q's. So we just copy down the P and the Q columns. Then we start at the innermost part of the expression, which would be this parentheses. So we use the conditional truth table. The conditional truth table says that the only time the conditional is false is if the first one is true and the second one is false. So that's my only false result. False. All the other ones are true, according to the rules. Okay, the next thing we do is we apply the results from this logic argument with the P. So we do all the premise stuff first. So what we're going to do is we're going to compare the results of this column with the values in this column. So it's basically what's the result of the operation in the parentheses. That's the result. Then we have an AND statement. So then we use the rules for AND. The AND statement says that the only time the AND statement is true is if they're both true. So we've got two trues there, so that one's true. We look down, each one of those has at least one false. So these are all false. And then once this column represents the result from the entire left-hand side, or the premises, you compare that with the right-hand side that still hasn't been touched, and you put the results in here. Then we're going to apply the if-then statement rules, the conditional rules. So again, we put, and when I was working the, just as a hint, when I was working the review, I was putting my fingers on the screen. So put your fingers, you know, you can't see me doing my fingers because I have them on my computer, but, you know, don't say, oh, I can't use my fingers. So if I compare these two columns, I've got two. So the only time an if-then statement is false is if the first is true and the second is false. Well, you can see I have no incident. I have no cases in this case. I have true, true. I have false, false. I have false, true, and false, false. So these are all true. So that's my result. They're all true. Well, it turns out that using this technique, if the final column that you end up with when you do the whole truth table, if they're all true, so in this case that's true, so since the result has all trues, the argument is valid. So you don't have to think too hard. You just look for all truths. And all truths is called a tautology. Tautology. Okay. It's just a special name for a truth table that has all truths. So that's pretty much it. We're just going to do some more examples as we go through. But that's the basic procedure. Now, when I did this, I'm like, why? You know, the first time you teach it, like, okay, I understand what's going on here. But why is that? Why does that work? Why does filling out a truth table, ending up with all truths, make it work? And I have not found a good explanation. So I actually tried to do some research on why is it that when you get all truths, it is a valid argument. And I've not found anything that's satisfying. It's true. It works. Okay, that's all I can tell you right now. It works. It is a valid method for determining whether an argument is valid or not. I mean, you can say sort of. Yeah, I mean, it sort of makes sense, but it sort of makes sense, but I haven't found anything that proves to me that this, what the proof would be to show that this is true. But it is true. So we're going to take it as that fact. So don't ask me, how do you know that's true? All I know is, what's that? Well, probably somebody has proved it, but I couldn't find any. Yeah, okay, so we just did that. So we just did the procedure. It's in your book if you forget. Assign a letter to represent each component statement of the argument. Express each premise and the conclusion symbolically. Form the symbolic statement of the entire argument by writing the conjunction, which is the and, of all the premises. So you connect all the premises by ands as the antecedent. So that's the if part of the if-then statement of a conditional statement, and the conclusion of the argument as the consequent. So that's what we did. You may not seem like that's what we did, but we took each premise, we connected it by the and, we grouped that together with a bracket. We then pointed that arrow to the conclusion, which is called the consequent. You complete the truth table for the conditional statement for the big long truth table statement. If it is a tautology, which means they're all truths, then the argument is valid. Otherwise, if you don't have all truths, if you have just one false in that whole table, that makes the argument invalid. So we're just going to look at some more examples. Now you can do it by looking at a specific example like we did before, which was Julie Nem, or you can just look at a general type of argument. So that's what we're going to do now. We're going to not use specific words. We're just going to look at the how you construct the truth table and make the truth table and then see whether the final result is all truths or not. So some of your homework problems say use a truth table to determine whether the argument is valid or invalid. So this is a conditional statement. This is the opposite conditional statement. And the conclusion is a compound statement. So to construct the final thing that we're going to make a truth table out, you take the first part, the first premise, which is if P then Q. You connect it with an and to the second premise. Then you group those together. That's your premise. Then that's the antecedent. What do they call it? Yeah, the antecedent, I think. That's the antecedent of the conditional. Then you put the conclusion on the right-hand side. So that's the truth. It gets long. So what we'll do is we will fill out the truth table and then see if we get all truths or not. And if it is, then it's a valid argument. So what I'm going to do is I'm going to copy that to the next page. So let's think about this. we need 5 rows because we have P and Q. So, then columns, we need 2 columns for P and Q. We need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 columns for the argument. So 11 plus 2 is 13. So we'll need a 5 by 13. 5 by 7. So it's going to get kind of big. So that should be 5 by 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So put that on one page. P, Q, when you get this complicated in an argument, it's easy to get confused about whether all the things are related to each other, and that's why using the truth table method will allow you to answer the question without getting completely confused. It's just a fairly straightforward method. So we'll just finish this up, and then we'll call it a day. So I'm not going to say anything until I finish filling out the easy stuff. Okay, so that's all the easy stuff. Then I would do these two because they're both in parentheses. So this is an if-then statement. So this is true. All these are false. Do the same thing here. So this one's, oh, I did it the wrong way around. I did it wrong. Wrong rule. This is false. These are the true. Okay. Go down this one's false because it's true, false. This one's true. Those are both the conditional. These are both conditionals. Then you compare these two columns and put the result right there. So this is an and statement. So true, true is true. These, the first and the last are true because they're both true. All the other ones are false. So that's the result to the entire left-hand side. I need to go over to the other side here and put in the result. So I use the and statement rules, which says that the and statement is only true if they're both true. So that's true, and the rest are false. And then finally, I compare this column, which was the last one I filled out on the left-hand side, and this column, which was the last one I filled out on the right-hand side. And then I apply the conditional rules for the conditional. So I see that I have true, true, false, 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 true, false. So this one is false. All the others are true. And because I didn't end up with all trues, it is not a tautology. Therefore, the argument is invalid. Whatever that original argument was, we don't know what the original argument was, but if you used that reasoning, it would be invalid. Just because you get one, all you need is one. It's like if you get one bad thing, you're one false. You can have 10 falses or 2 falses or 1 false. 1 false ruins it for the whole thing and means that it's invalid. So this is since we didn't get all trues, the argument is invalid. So I'm not going to assign any homework from this section yet, even though you probably could do it, just because I've already assigned stuff already. So we'll see you on Wednesday. If you have, and Harley's going to see me